Okay, let's get into the heart of the matter. Again, we're going to start off kind of slow, and then we're going to get into a lot of design detail. We're going to start off with just some basics. We're going to actually start off with some water quality treatment. And this was feedback from other courses that people wanted to hear about that first, so we'll do that. So here's the components. You can see the list, flow entrance. There may be pre-settling. For example, if you move to larger road systems, you're managing water off of arterials. There can be a large sediment load associated with that water coming in, and you very likely want some kind of pre-treatment or pre-settling. So that can be very important as far as the long-term function of these systems, particularly in high-use areas. Arterial compared to roof runoff, for example, off a single-family home. Pre-settling, very important for those high-use areas. There's a corresponding area. Generally, that's 6 to 12 inches in our world. The bioretention soil, if you like, I guess, uncertainty. There is a tremendous amount of research going on around bioretention soil media right now, and we, as a region, this is interesting, we're implementing while we're still figuring out how this stuff, the intricacies of how this stuff works. So we're Herrera and some others, actually Herrera is doing most of the research in the region, understanding how our current specification for bioretention behaves for water quality treatment. We're in the middle of developing new high-performance bioretention media. We're right in the middle of developing a lot of research, data, and information around that, and on the way to developing some new bioretention media specifications. They're high-performance water quality treatment guidelines. Mulch and compost on top. Coarse vegetation, yes, vegetation is important. We get the question all the time, do you really need vegetation, or should, well, if you don't, you pretty much have a sand filter. Yes, vegetation is an integral part of it. Filter fabric. In general, we do not recommend filter fabric between the media and the subgrade. Now, there may be a need for geotextiles if, for example, you have a sidewall, particularly if you might have a vertical sidewall, and you have some sensitive infrastructure that you want to reduce the infiltration towards that sensitive infrastructure. So there are times when you may need some sort of geosynthetic, but in general, the separation between the media and the subgrade with geotextile is not needed. It's a frivolous cost, and it potentially creates a clogging layer. Especially if you don't know you don't prescribe the right filter fabric. I should qualify that. Liners, of course, may be needed if you have contaminated soil underneath and you're just treating water through the bioretention area and discharging it through an underdrain. But as far as just separation between the media and the subgrade, and you're trying to infiltrate in the subgrade, we really strongly recommend not using a filter fabric there. Underdrains, maybe, maybe not. We'll talk more about that when you need them and how you can use them to your advantage. And then overflow. There's always an overflow. You have to have an overflow. Even in a rain garden, sitting in the front yard. A little bit on the difference between bioretention and rain gardens. Bioretention will often include, doesn't have to, but often include surface and subsurface infrastructure like underdrains, overflows, and all that. Bioretention, it is required that you have a designed media that meets the current specification in the Stormwater Management Manual or equivalent. I'll tell you right now, we'll look at some data, but the current specification for bioretention media, we now can say with high level of confidence that for the first 1, 2, 3 years, perhaps more, flushes phosphorus. That's a very bad thing for Lake Whatcom. So that's an issue we're working on right now. That's some of the research we're doing right now, is how to get rid of that flushing characteristic. Design soil mix. Bioretention meets requirements for MR 6 and 7, flow control and water quality treatment, and 5, if you're in the situation where you're meeting 1 through 9. Now I know that's really complicated language there, but basically bioretention is when you're, often case when you're implementing bioretention, you're in this scenario of 1 through 9, minimum requirement 1 through 9, so those larger thresholds we talked about, right? Rain gardens, on the other hand, and I should say for bioretention, stamped by an engineer. So that's another requirement. If it's a bioretention area, it's going to have an engineering stamp. So that's the difference. Rain gardens, likely, oftentimes don't include surface or subsurface infrastructure. There's just, simply infiltration to the subgrade. There's less restrictive soil mix guidelines. There's actually no particular set guideline. So you have a lot of flexibility with the media that you use in a rain garden. In fact, it could be the dirt you've excavated out of there and you put some compost in it, or maybe some sand and compost. So a lot less restrictive as far as the soil guidelines. And this is for meeting MR, minimum requirement 5. All right? Typical application there would be a single family lot. Right? So these could be very effective. I mean, no infrastructure, infiltration of the subgrade doesn't mean it's less effective. In fact, that's a great scenario. That's optimum. So it's just that this is the division that we have that has been created for us, for Western Washington. Primary functions for bioretention and rain gardens: the hydrologic benefit, flow attenuation, volume reduction, water quality treatment. We're still working on this one. And we can now say that with the bioretention media that we're consistently seeing the flushing of nitrogen, phosphorus, and copper from bioretention media. The 60% sand, 40% compost. We've tested it over and over and over again. And the last research project we just finished, we see it again. And however, that might not be a problem, depending on your setting. If you're infiltrating to the subgrade and that subgrade soil is a good receptor, in that case, nitrate would probably might be your biggest issue. Phosphorus could be your issue if you're proximate to a phosphorus-sensitive water. And there are now guidelines, right? There's a memo from Department of Ecology about restrictions of where you can use the current bioretention media in proximity to sensitive receiving waters. But that 60-40 mix might be fine. It might work beautifully depending on your setting, if you're infiltrating to an adequate subgrade. Then again, it might not be. And if you have an underdrain to a receiving water, you have to think very carefully right now about where what media you're using, how you're applying it. And then the third one, and I get some pushback on this. Third one, aesthetic amenity. And people say, yeah, why is that? Is that a primary goal for bioretention? And I would argue yes. Because, for example, take City of Seattle. And the program manager at City of Seattle, when she's talking to the mayor says to her, how do they look? These need to look good. We're putting these in people's front yard, along their roads, where they park, this, that, and the other. They have to look good. If they don't look good, we're not doing it. So I would say in some cases, certainly, in most all applications, if we're putting these things in people's front yards and right along our streetscapes, we need to work at making them look as good as we can, designing them so they're an amenity, not a liability. So a little difference between bioretention and biofiltration. This is an area where there's often confusion. So in a bioretention area, the flow path primarily is vertically through the media. That's where we get our treatment, and that's the course of water for flow control as well, to either the subgrade or to underdrain with perhaps a control structure or an orifice. And we primarily think about our treatment goals from volume infiltrated, right? 91% of the annual runoff file. That's our treatment, our treatment goal. Bioretention is not biofiltration or say a bioswale that is primarily surface flow through vegetation. It's rough, vegetation. There's filtration through that swale. Surface, horizontal flow as opposed to vertical flow. That's a big difference between the bioretention and biofiltration. There, we primarily think about treatment goals and our modeling in residence time. Hydraulic residence time is important in bioretention for treatment, but that's not some of the primary modeling and design approach that we're thinking about when we're designing. So definitions around bioretention: shallow landscape depressions that are engineered bioretention, could be non-engineered, rain garden, to receive stormwater from small contributing areas. So this is critical, and there are guidelines in the Stormwater Management Manual that promote that. That as for you guys designing, that push you that direction in the correction factors you use. There's thresholds as far as the contributing area to bioretention areas where you can use a smaller correction factor rather than a larger, 2 rather than 4, if you're under certain thresholds for the contributing area. That's purposeful in the Stormwater Management Manual. We wrote that in to promote the use of this approach for small contributing areas. And there's very large advantages to designing with small contributing areas. Dispersed, small scale. We've got cells, swales, planters, planter boxes, and then online, offline, that's something that's a little more obscure, and I'll show you a picture of that, and we'll be done with it. You don't see a lot of that, this sort of online, offline approach much in this region, if any more in the U.S. Cells, shallow, vegetated depressions. Gentle side slopes, right? Often 3 to 1. These are, standalone cells, not so much, not really a conveyance structure. And again, optional underdrains and control structures. But I would say 10 years ago, when we were talking about using control structures, orifices, and other more sophisticated control structures for bioretention, the region was generally, no, that's an added complexity. You might clog, the orifices, they might clog, all of that. I'd say we're warming up to that now in this part of the world. We're starting to see more interest in using control structures and the thinking of higher flow media with a control structure. I think there's just generally more acceptance, perhaps adopting that kind of approach. And there are advantages and disadvantages to all these things, but I think we're seeing a warming in general to control structures in bioretention. Swales, same as cells really, but they're interconnected. And there are various ways to interconnect them. And planters, you would see these implemented primarily in ultra-urban areas. This is a picture of 12th and Montgomery and Portland, and then a mystery Seattle planter in the bottom. I can't remember where this one is. Vertical walled, open bottom to allow infiltration to that subgrade. And again, could have control structures. Now the planter boxes, same thing, they're just fully enclosed. So these are the definitions we've adopted for this part of the world. Planter box, fully enclosed, so what? It has to have an underdrain, right? You have to design that in. And again, control structure may or may not have a control structure. This offline, online approach, this is an old shot. This is one of the first bioretention areas built in the US back in the East Coast. And it's a little hard to see, but there's right along the road, there's a swale, I have a gentle swale. And then where those yellow flowers are planted, that's the bioretention area. The inlet is off the swale, and the inlet is the same as the outlet, right? So that's the control. Water flows to a certain level, and then it starts to backflow out. And you don't see a lot of this approach, but it is out there and used occasionally, and it can work quite well. You often need quite a bit of space, and we're often building on small lots now, and it gets, in the East Coast, this quarter-acre suburban lot is typical. Quarter-acre anymore in a lot of parts of Puget Sound is urban Puget Sound is getting pretty rare.